I'm Dr. Chris Creighton, and in this video we'll be talking about function composition, which the core idea is plugging one function into another function. The base idea here is you're going to be able to interpret a composition of two or more functions in all types of representations of a function. So the key ones here are a list of points in either a table or list form, or using an equation or a correspondence to compose these functions. So what exactly is functional composition? And this is the core idea. So in each of these, I have three different blobs here. And these blobs represent the correspondences of given functions g and f. So this is given as a correspondence. So this is honestly how I think about functional composition, is where you take one function and plug it into another function. So for instance, if I have a value here, I'm just going to call it x. X is in the domain of g. So it's something over here. And being g, g sends this value x to some other value here. And we're going to call that g of x using our functional notation, which is really important for these types of problems. If you're not comfortable with it, please go back and review the previous content on it. So here we have something that goes from the domain of g into the range of g. But fortunately, the range of g lives also in the domain of f. So then what does f do then? Well, it takes the given value in its domain to a certain output. So it takes this value here and sends it over here. So this is the functional point, f of g of x. So it takes a value, g of x, and takes it into its own range of f. And this basic idea, going from the domain of g into the range of f by just plugging in the output, g of x, in the domain of f, into the function f to figure out what we get, is called functional composition. And it's denoted that f of g of x, so this x is in the domain of g, this is written as f of g of x. So this is called f of g of x, if you would. And that's the notation for it. Do not get this confused with functional multiplication, where sometimes there's a dot there. This is going to be an open circle. Open circles for functions denotes functional composition, and you plug in the function on the right into the function on the left. So f of g means you take the functional g and you plug it into f of g. So what does this look like with polynomials? So there's many ways to compose these things. So let's just start off with one. Let's just do g of f of 2, or something like that. This means that we take the value of f of 2, and then plug it into f. So the first thing we need to do is figure out what is f of 2, which is really nice. So f of 2 is equal to 2 times 2 minus 1, which is equal to 3. So we plug in the value 3 into the function g. So this is equal to g of 3. Which is rather nice, because now we need to evaluate g of 3. So we know the value, the equation of that. So now we just need to evaluate that. So that is equal to 3 squared plus 3, which is equal to 12. So g of f of 2 is equal to 12. And that's because f of 2 is 3, and then g of 3 is 12. It is taking the input 2 into the function f, outputting 3, taking the input now 3 into the function g, and outputting 12. So you're literally taking the function f and plugging it into g. Another thing that we can do is we can do things like f of let's see here, just -1. We'll see what this does. So this is equal to f of minus 1. So I'm just taking the function f and plugging it into f. So the first step here is figuring out what f of minus 1 is. Well, that's going to be 2 times minus 1 minus 1. Well, that's going to be negative 3. So this is equal to f of negative 3, because that's what we just found. That's the output of f at negative 1. Well, what's f of 3? So f of negative 3 is going to be equal to 2 times minus 3 minus 1, which is equal to minus 7. So f of negative 3 is equal to minus 7. So if we were to plug in the function, or the value negative 1 into the function f, and then take that value and plug it back into the function f again, so essentially just plugging f back into f, we will get the value negative 7. So like functional algebra, when the functions are given as equations, you can plug in one equation of a function into the other one, and then you might need to do some algebra to simplify it down. So for instance, if I am to do g of f of x, and so what that means is I'm plugging the equation of f of x into g of x. So this is going to look a little bit complicated. So in this case here, this is equal to g of 2 minus an x, or 2x minus 1. So I took the equation here and popped it in to give us g of 2x minus 1. So all this is saying is that we're going to input now the function 2x minus 1 into the equation for g. So this is now going to be equal to replacing all of the x values in g by this input here. This is going to be equal to 2x minus 1 squared plus 3. So I literally replaced x by what I plugged into g. So the 2x minus 1 goes into the function g. And this is now a new functional expression for g of f of x. So g of f of x is equal to x, or 2x minus 1 quantity squared plus an additional 3. Which, if you might need to multiply this out. So this is equal to a 4x squared minus 4x plus 1 plus 3, which is equal to 4x squared minus 4x plus 4. So not too bad. Now we could do similarly with the other one. So how about we do f of x? So we're going to plug in the function f of x back into f of x. So similarly, this is f of x. I always write this down because I always want to make sure I'm plugging the right function into the right function. So in this case here, this is equal to f of 2x minus 1. So likewise, f of x is equal to 2x minus 1. So I'm going to take 2x minus 1 and plug it in there for our x. So this is equal to 2 times 2x minus 1 minus 1. So I replace the x there by a 2x minus 1. Using parentheses here is key and crucial, particularly where you have several terms here. Because now if I'm to simplify this, I need to distribute that 2. So this is equal to 4x minus 2 minus 1, which simplifies rather nicely to 4x minus 3. Again, much like functional algebra when we were adding and subtracting functions from table, there are some nuances to doing the same thing from the table for functional composition. So let's try one. So let's do f of g at the value 2. So in this case here, I would write this as f of g at 2. Again, right to left. So what is g of 2? G of 2 corresponds to going to 2 on the x column and then finding the value here. So g of 2 is equal to 1. So this is equal to f of 1, coming from this 1 here. And then f of 1. Well, f of 1, the way I honestly think about it, we're plugging the g of 2 into here. So f of 1 means you go to 1 now on the x row for the f table, and then read off the value here, 1. So that is equal to 1. So that's what I mean is like you take one function and plug it into the other. The outputs of the innermost function turn into the inputs of the outermost function. So let's try another one. How about g of f at 1? So in this case here, this is g of f at 1. Well, we just noticed that f of 1 is equal to 1, so this is g of 1. So the basic idea here, if I do this in a different color, is I come here to 1, get f of 1, come over here to the input 1, and then read off the value there as 2. So that's honestly how I think about it. So I again go, okay, we're doing f of 1. F of 1 is 1, so now the output 1 goes back into the inputs of g, 1, and g of 1 gives us 2. So then as another example, how about f of 0? So in this case here, writing this is f of 0. Well, f of 0 from this table here is equal to minus 1. So this is f of minus 1. So much like in the original table, when we were adding the two functions together and we got something that wasn't in a valid input, f of 1 is undefined. There is no value assigned to f of negative 1. Negative 1 might be a good number to plug in, but you just don't know any information about the output at negative 1. So on the table here, we would have minus 1 here and then just a big old question mark. We have no idea what this is. So it can happen that you can plug something into the innermost function and then not be able to evaluate it in the outermost function just because it's not in the domain of the outermost function. The outputs of the innermost function must be in the domain of the outermost function. They must like compose well together. So that's just a big word of warning here. If you see something like this, f of negative 1 is completely undefined because f has no value associated to negative 1.